Hello, good evening. I am Saurabh and I welcome all of you to this session for the NPTEL course IC Engines and Gas Turbines. This is our session 5. And in this session, we will discuss some problems related to fuel injection systems and combustion in spark ignition engines and compression ignition engines. Okay, so we will begin our session with question number 1. Okay, so here is question number 1. Question number 1 says, at okay, so question 1, it says at which stroke the fuel is injected in CI engine. CI engine means compression ignition engine. So in which stroke fuel is injected? So as you know that there are 4 strokes, right? It is a 4-stroke engine: suction stroke, compression stroke, expansion stroke, and exhaust stroke. And we know that fuel is injected near the TDC, but not exactly at TDC. So it is injected a little before TDC. Okay, so at the end of compression stroke, okay, near the end of compression stroke, fuel is injected in CI engine. Okay, so correct answer should be option B, compression stroke, right? Correct. Okay, so I hope there is no doubt in question 1, and we can proceed to question number 2. Question number 2, which of the following is the characteristics of CI engine fuel? Sorry, SI engine fuel, spark ignition engine fuel. So there are 4 options: sulfur content, gum deposition, volatility, or all of the above. Okay, so I hope you can easily answer this question. So which option should be the correct option? So sulfur content. Sulfur content is basically very important, characteristic of the fuel, because if there is more sulfur content, then the sulfur content basically tends to reduce the auto ignition temperature, right? So if there is more sulfur content, then auto ignition temperature of the fuel will be reduced. And if the auto ignition temperature of the fuel is reduced, then the fuel will be more, prone to knocking, right? So sulfur content should be very less or zero. Okay. So yes, it is a characteristic of SI engine fuel. Option B says gum deposition. So yes, it is also a characteristic, because if you know, because we know that if there is unsaturated hydrocarbons, and after a long time, those unsaturated hydrocarbons will be, converted into saturated hydrocarbons, and that will be like a thick deposition, like a gum deposition. Okay, and that gum deposition can take place at that gum deposition can take place at intake valves, and if there is a carburetor engine, then on the carburetor itself, or if it is a fuel injector PFI, then on the injector. Okay, so we don't want that, right? And volatility as the name suggests, it shows how volatile a fuel is. Okay, so if the fuel is very less volatile, then it will not be evaporated easily and it will not get mixed with the air, right? So we want that fuel should be volatile so that it can get easily mixed with the air, right? Okay, so all these parameters are important, and the correct option should be option D, right? All of these. And volatility, it should be not very low or not very high. Okay, if it is very low, then uh, fuel will not be evaporated and will not get mixed with the air. And if it is very very high, then it can evaporate from the tank itself, right? There will be there is tank in which you fills the fuel, and if it is very very volatile, it will get evaporated, right? So it should not be very volatile, and but volatility is important, right, for fuel air mixing. Okay, now we can move to question number 3. Question number 3. In a SI engine, the correct order of the fuels with decreasing detonation tendency. So detonation basically means knocking. Okay. So there are certain family of fuel: paraffins, olefins, aromatics, and naphthalenes. Naphthalene. So in the lectures, all these things have been discussed, right? All these types of fuel have been discussed. So paraffin, what are paraffins? Paraffins are, saturated carbon chains, right? And no double bond, no ring. Okay, these are paraffins, right? And olefin, there can be one double bond, right? So these are certain families of the fuels. Okay, and we have to tell the order, the decreasing detonation tendency. So you know that paraffins are most susceptible to auto ignition, right? These can be easily auto ignited, right? So that is the reason these are the ideal fuels for CI engines, right? So there are long hydrocarbon chain and there are a lot of sites which can promote the auto ignition, right? So paraffins have most detonation tendency. And aromatics, these are very very stable, so they don't want to undergo any reaction, right? So auto ignition will also be not easy. Okay, so they are less susceptible to auto ignition, so they have least detonation tendency. And olefins, since they have one double bond, so they are unsaturated, so they have tendency to get saturated. And as compared to naphthalene are little more stable, but olefins are olefins have more detonation tendency, right? So if you write the octane number, then Aromatics will have highest octane number, then naphthenes, then olefins, and then aromatics. Okay. So option B should be the correct option. Okay. So this question be framed in another way, like arrange these fuels in order of decreasing or increasing octane number. Okay. So paraffins will have least octane number and aromatics will have highest octane number. Okay. I hope this is clear. Okay. Is there any doubt? If there is no doubt, then we will move to question number 4. Okay, so for question number 4, we have some information, some data. Let's read that. A single cylinder 4-stroke diesel engine uses 2.4 kilogram of fuel per hour. Engine speed is 1000 rpm. The density of fuel is 900 kilogram per meter cube. Fuel injection time period is 0.0015 second or 1.5 millisecond. If the average injection pressure is 14.8 megapascal and charge pressure during the injection is 2.14 megapascal, the discharge coefficient of orifice is 0.89. The duration of nozzle open crank angle in degree is. So some information is given. So what is given? That this is a 4-stroke diesel engine. Fuel consumption rate is given. Engine speed is given. Density of the fuel is given. Fuel injection time period is given. Okay. And injection pressure is given. And charge pressure means pressure inside the cylinder, right? During the compression, the charge has been increased. The pressure has been increased from atmospheric pressure to this pressure. Okay. So this is the in cylinder pressure. At this pressure, the fuel is injected. And discharge coefficient is given. We have to find for how much time the nozzle hole will be opened. Okay.
Nine degree, sir.
Hmm?
9 degree.
Okay, let's calculate and then we will verify. The fuel injection time is 0.15 second and this time is in seconds, right? We have to tell in terms of CAD, right? Crank angle degree. Okay. To convert this time in crank angle degree, so what will we do? So 1000 rpm is the engine speed. So 1000 rpm means 1000 revolutions per minute, right? So this means 1000 into 360 degrees per minute, right? So this means 1000 into 360 divided by 60 per second, right? So this is the engine speed. So this is engine speed. So 6000, right? 6000 degree per second. Okay. And time is given, right? Injection time is given 0.0015 second. So in terms of CAD, it will be 6000 degree. multiplied by 0.0015 seconds. So it will come out to be 9 degrees, right?
Yes,
So
sir.
9 degrees, this would be the correct option. Okay.
Yes.
So now question 5, this is also based on the previous data. The gas flow velocity of fuel injected through the nozzle is. So we know what is the gas flow velocity of fuel. So we know that it is given by under root 2 delta P divided by density, right? This has been discussed in the lecture, right? So delta P is the pressure difference. Is the pressure difference. Pressure difference means injection pressure minus in cylinder pressure, right? So injection pressure is given 14.8 megapascal. And in cylinder pressure is 2.14 megapascal. So this is delta P, right? And density rho, it is given 900 kilogram per meter cube. So velocity will be rho 2 into 14.8 minus 2.14. So it is in megapascal. To convert this in SI unit, just multiply by 6 divided by 900. Okay. So you can calculate this value. Under root into 14.8 minus 2.14 into 10 to the power 6 divided by 16
167.72.
167.73 meter per second, right?
Yes.
So which option? Option D, right?
Yes.
So again, one more question based on the same data. Calculate the diameter of the fuel orifice. Okay, we have to now calculate the diameter. So if the diameter is D, then you can calculate the mass per cycle, right?
Yes.
Mass injected per cycle. So this will be what? Area into time into density into velocity and coefficient of discharge, right? This will be mass injected per cycle, correct? Right? And what is given? Per hour mass fuel consumption is given. Okay. So how much it is? 2.4 kilogram per hour. 2.4 kilogram per hour. So in 1 hour, how many cycles will be there? That we can calculate, right? Engine speed is given, that is 1000 RPM, revolutions per minute. And since it is a 4-cycle engine, and we know that one cycle takes 2 revolutions, right? Correct. So 1000 revolutions per minute means 1000 divided by 2 cycles per minute. Correct. So this means 1000 divided by 2 divided by 60 cycles per into 60 cycles per hour. Okay. So now we have number of cycles in 1 hour, right? So 30,000 cycles per hour. So it is not coming. So in 1 hour, there are 30,000 cycles and 2.4 kilogram fuel is consumed in 1 hour. Okay. So in one cycle, 2.4 kg divided by 30,000, right? So this will be fuel consumption in one cycle. Correct. Right. And from this expression that we have just wrote, that mass injected per cycle, this should be equal to coefficient of discharge multiplied by the area. Area will be pi by 4 d square times fuel injection time into density into speed, right? So all these values we have, we just need to substitute. Correct. So 2.4 divided by 30,000 will be equal to CD. How much is CD? Do you want me to sorry. Okay. Coefficient of discharge is 0.89. 0.89 times pi by 4 d square into delta t. How much was delta t? 0.0015. Into density was 900 kilogram, I think. Yes. And velocity we have just calculated, and it was 167.73. 167.73. Okay. So this will give the D. Okay. So can you please calculate how much it is?
Yes. 0.5.
So I'm getting 0.00071 meter. So 0.71 mm. Okay, so you are getting the same. So this should be the nozzle hole diameter. Correct? So is there any doubt?
No, sir.
Okay. So now question number 7. It says a SI engine operating at 1200 RPM has 10.2 centimeter bore with spark plug offset by 6 mm from the center. The spark plug is fired at 20 degree before TDC. It takes 6.5 degree of engine rotation for combustion to develop and get into flame propagation mode, where the average flame speed is 5.8 meter per second. We have to find the time for one combustion process. So that basically means the time for flame front to reach the farthest cylinder wall. Okay, you got the question? Hello?
Yes, sir. Speed.
So question is saying that there is a SI engine, spark ignition engine. Engine speed is given Bore is given. Bore is basically cylinder diameter, right? And spark plug offset is 6 mm from the center. Okay, so spark plug is not at the center, right? So there is some distance between center and spark plug, and that distance is given how much? 6 mm. So let us say this is the cylinder and this is the center. So the spark plug is somewhere here. Okay, this is the spark plug. So this distance is 6 mm. Now when this will ignite and the flame will be developed, so it will propagate, and the furthest point is on the other side of the cylinder, right? So this is the furthest point, right? Up to here it need to reach, right? So how much this distance will be? How much distance flame need to travel? Distance for flame to travel is radius plus this offset, right? So 10.2 centimeter divided by 2 plus 6 mm, right? So 5.1 centimeter plus 0.6 centimeter. So it will be 5.7 centimeter. So this is the distance that flame need to travel. Okay, fine. It takes this much engine rotation, 6.5 degree of engine rotation for combustion to develop. Okay, fine. With the average flame speed is 15.8 meter per second. Flame speed is given, right? Flame speed is given. Average flame speed is given. How much? 15.8 meter per second. Okay. So now we have distance, we have time. So sorry, we have distance and we have speed. We can calculate the time, right? So you can calculate time of flame travel. So it will be distance 5.7 centimeter divided by 15.8 meter per second. So just convert this thing into meter. So we'll get the time. Okay. 5.7 divided by 15.8. So 3.607 into 10 to the minus 3 second. Correct? 3.6 millisecond. Okay. Engine speed is given 1200 RPM. 1200 RPM. So this means 1200 revolutions per minute. So this means 1200 times 360 per minute, right? So this means 1200 multiplied by 360 divided by 60 per second. Okay, so this is the engine speed in degrees per second. And time for the flame travel we have. So time for flame travel in CAD, time of flame travel in crank angle degree. So this will be 1200 into 360 degree divided by 60 into 3.6 into 10 to the power minus 3, right? So how much it will be? So this will be 1200 times 6 times 3.6, right? So 25.92 degrees, right? So this is the time of flame travel in CAD. Okay. So this is the time when the flame has been developed, right? But it takes some time for flame to develop. Okay. So it takes 6.5 degree of engine rotation for combustion to develop and get into flame propagation mode. Okay. So this is the ignition delay, right? So this is the ignition delay. This is 6.5 degree, right? So total time from the start of spark or ignition to reach the farthest point. So this will be 6.5 plus 25.92. This will be total time, right? So how much it will be? So this is the time taken for travel, and this is time for the development of flame print, right? 6.5 plus 25.92. So this comes out to be 32.42 seconds. Sorry, degrees. Everything we are doing in degrees, right? Shaft rotation. Okay, so what we had to calculate? We had to calculate time of one combustion process, the time for flame front to reach the farthest cylinder wall in second. So in seconds, we can easily convert this thing into seconds, right? To convert in second, what will we do? How much is the engine speed? 1200 RPM. 1200 revolutions per minute. Again, 1200 into 360 degrees per minute, right? So this means this means 1200 into 360 divided by 60 per second. Okay. So in 1 degree, for 1 degree, what will be the time? 1 divided by 1200 into 360 into 60, right? This will be the time for 1 degree, right? So for 32.42 degrees, so this is the time, right? Total time 60 into 32.42 divided by 1200 into 360. So this will be time for one combustion process, right? From the start of the ignition to the time when the flame point reaches to the farthest cylinder wall, correct? So just calculate this. 60 to 32.42 divided by 1200 times 360, right? This comes out to be how much? 0.0045 seconds, right? Or 4.5 millisecond, right? So this is what we had to find. So this was asked, right? The time for one combustion process. Okay. Now, second part, it says crank angle position at the end of combustion. So when the combustion will be completed? So first of all, there is a spark plug, right? And it is given that a spark plug is fired at 20 degree before top dead center. Okay. So before 20 degree from the top dead center, a spark plug is fired. Then there is some delay. There's some delay of 6.5 degree for the flame to develop, right? Now flame is developed. Now it will take some time to reach the farthest point. Okay. So the total time taken from the firing of spark plug to the total to up to the point when it reaches the farthest point, so that we have to find, right? And that we have I think already find, right? This is 32.42 degree, right? So it is started at 20 degree before the top dead center, right? So spark timing is 20 degree BTDC before top dead center. 6.5 degree is the ignition delay, and 25.92 degree is the flame travel time, right? So everything you can write in terms of degrees, and instead of before the TDC, let us write it in after TDC. So in terms of after TDC, it will be minus 20 degree after TDC. Okay. So that so the crank angle position at the end of combustion will be CAD position at the end of combustion will be what? Minus 20 degree plus 6.5 degrees plus 25.92 after TDC. Okay. Minus 20 plus 6.5 plus 25.92. So 12.42 degrees after top dead center. So this will be the CAD position. When the combustion will be completed, right? Is this correct? Hello? Can you please cross check? Hello. Okay, you please cross check, and if there is any mistake, then please let me know. But this is how we will calculate, right? Okay. So all the things, most of the things we are calculating in terms of crank angle degree, right? Why? Because if you are calculating these parameters in time, seconds, then at higher speeds, uh, there will be less time, right? For any process, and for lower speed, time will be more. So if you want to compare, these things at two different speeds, then it will be difficult, right? If you are calculating these things in second, but if you are converting all the parameters in cat, then it will be easy for comparison purpose, right? Okay, so I hope this is clear, and we can move to the next question. So should we proceed for next question? Hello, am I audible?
Yes, sir.
Okay, so is this clear? Previous question, is there any doubt in previous question? Hmm? Hello. If there is any doubt, please ask, or we will proceed to question number 8. Okay, I hope there is no doubt, and let us go to question number 8. It says a four-stroke engine using 0.272 kilogram per kilowatt hour, fuel of 32-degree API, develops 15 kilowatt per cylinder at 200 RPM. The fuel injection pressure is given, it is 120 bar, and the combustion chamber pressure is 30 bar. If the duration of injection is 30 degree of crank travel and velocity coefficient is 0.9, determine the diameter of the fuel orifice. We have to find the diameter of fuel orifice, and some data is given. So if you understood what question is saying, then we will proceed. So is there any doubt what question is saying? Hello. Okay, let us read it again. One four-stroke engine, okay, using 0.272 kilogram of fuel per kilowatt hour. Of fuel 32 API, and it develops 15 kilowatt per cylinder at 2000 RPM. Fuel injection pressure is given 120 bar, and combustion chamber pressure is given 30 bar. And duration of injection is again 30 degree of crank travel, and velocity coefficient is given. We have to find the diameter of fuel orifice. So all these parameters, you know the definition, right? The only new thing I think, maybe API, right? You know API. So API stands for American Petroleum Institute. And this 32 degree API basically means the specific gravity. Okay, so this American Petroleum Institute has given certain rules to define the specific gravity of a fuel. Okay, for example, the fuels which have API more than 10 degrees, they are lighter than water, and the fuels which have API less than 10 degrees, they have heavier than water. Okay, so in terms of water, uh, this API is defined, and this formula is also given to find the specific gravity. So first of all, let us find the specific gravity. So specific gravity, this is given by 141.5 divided by API plus 131.5. In our question, API is given to be 32 degrees, right? So we can find the specific gravity. So 32 plus 131.5. So how much it is? 141.5 divided by 32 plus 131.5. So specific gravity for this fuel, it is 0.865. Okay. So what will be the density? Density of the fuel? This will be 0.865 times 1000 kilogram per meter cube, right? This will be the density. Okay. The engine develops 15 kilowatt per hour. Okay. And injection pressure is 120 bar and combustion chamber pressure is 30 bar. Okay. So pressure difference or delta T will be 120 bar minus 30 bar. 120 bar minus 30 bar. So 90 bar is the pressure difference, right? Correct. What else is given? Duration of injection is also given. Duration of injection. This is given how much? 30 degree. Right? Now you can calculate the fuel consumption, right? Fuel consumption per cycle. So what will be the fuel consumption per cycle? See, what is given? It is given that it is 0.272 kilogram per kilowatt hour. Okay. So in 1 hour, for 1 kilowatt, it is consuming 0.272 kilogram of the fuel. Okay. And it is producing 15 kilowatt hour. Okay. So 0.272 times 15. So this will be the fuel consumption rate per hour. Okay, so in 1 hour, 0.272 times 15 kilogram fuel will be consumed, right? And engine speed is given. How much engine speed is given? 2000 revolutions per minute. Okay, and it is four stroke engine, and we know that in four stroke engines, for one cycle there should be two revolutions, right? In two revolutions, one cycle is completed. So in 2000 revolutions, how many cycles will be there? 1000 cycles will be there, right? 1000 cycles per minute, right? So 1000 cycle per minute means 1000 times 60 cycles per hour. Okay, so 60,000 cycles per hour, and fuel is consumed. How much fuel is consumed? 0.272 into 15 kilogram per hour. This is fuel consumption rate. Okay, so in one cycle, how much fuel will be consumed? 0.272 times 15 divided by 60,000 kilojoule, right? In one cycle, this much fuel will be consumed in one cycle, correct? So if you calculate this value, 0.27, sorry, 0.272 times 15 divided by 60,000. So it is coming out to be 1, 2, 3, 4, 5. 6.8 into 10 to the power minus 5 kilogram per cycle. This is the fuel consumption rate per cycle. Okay, fine. Now what else? We have to find the diameter of the fuel orifice. Okay, so for the diameter, we will use the same formula, right? Fuel mass injected per cycle, fuel mass injected per cycle. This will be the coefficient of discharge times area of the hole times density times velocity, right? Correct. Hello. Into time, right? Fuel injection timing in one cycle. Okay. So CD, it is given. Area, we have to find. Wall density, we have got. Now we need velocity and time, right? So velocity will be coefficient of velocity times 2 delta P divided by density. Okay. So coefficient of velocity coefficient is 0.9, 0.9 times 2 into delta P. We have just find it is 90 bar, and density is this, right? 0.865. 0.865 into 1000 kilogram, sorry, per meter cube. Okay, so this is the velocity. 0.865 into 1000, right? So it is coming out to be 129.8 meter per second. This is the velocity. Okay. Now we have velocity and time. Do we have time? Time in seconds. Injection duration is given 30 degree. Now we need to convert this 30 degree into seconds. Okay. So injection duration, it is given in CAD. Okay. 30 degree. We need to convert this 30 degree into seconds. So engine speed is how much? 2000 RPM. 2000 RPM. So this means 2000 times 360 degrees per minute, or 2000 into 360 divided by 60 per second. Okay. So this means for 1 degree is 60 divided by 2000 into 360, right? Seconds. Right? So for 30 degrees, 60 times 30 divided by 2000 divided by 60 seconds. This will be injection duration in seconds. Okay. So 0.00025 seconds or 0.25 milliseconds. This is the injection duration. Okay. Or T. Now we can substitute all these values here. Okay. So mass per cycle, this will be, CD is not given, so let us assume this to be D. Okay, sorry, 1. So mass injected per cycle will be area times rho. Rho is 0.865 into 1000 kilogram per meter cube. This is the density, and velocity we have just calculated is how much? 129.8 meter per second. Okay, and time we have just got 0.00025 seconds. This should be equal to this value, 6.8 into 10 to the power minus 5 kilogram per cycle, right? 6.8 into 10 to the power minus 5. 6.8 into 10 to the power minus 5. Correct. So from here you can go get the area, right? And area will be pi by 4 d square. So from here you can get d. So d will be 6.8 into 10 to the power 5 into 4 divided by pi into 0.865 into 10 to the power 3 into 129.8 into 0.00025, right? Under root. So this will be the nozzle hole diameter. So how much it is? I'm getting 175. So I think I have made some mistake. Actually, here is minus 10 to the power 5. Okay, let's write it again. Again, some error. Hello?
$11.82.
The answer that I have, uh, that is given 0.555 mm. So I think we have mistake somewhere. Let me quickly check. So is this time correct? One divided by 4,000. It is not correct. See, this zero will not be there, right? 60 will cancel out this thing and it will become. So this will come out to be 0.0025, right? Second. Okay. So T is 0.0025 seconds. We'll check all the values. Okay. And Okay, now let us do it. This is correct. 6.8 into 10 to the power minus 5. 6.8 into 10 to the power minus 5. This is kilogram per cycle. Kilogram per cycle, and that should be equal to area times density times velocity into time, right? So 6.8 into 10 to the power minus 5 will be equal to pi by 4 into d square into density is how much? 0.865 into 10 to the into 1000 into velocity. How much was the velocity? Velocity was 129.8 into time. What was the time? Time we have just got 0.0025. Okay, these are the values, and now we can find d is equal to under root 6.8 into 10 to the power minus 5 into 4 divided by pi into 0.865 into 1000 into 129.8 into 0.0025. Let us calculate this value. Okay. 6.8 into 10 to the power minus 5 into 4 divided by pi into 0.865 into 1000 into 1000 here, 1000 into 129.8 into 0.0025. Wow, this calculator is not working fine. I will use this one. Can you please calculate this? How much it is coming? Under root 6.8 into 10 to the power minus 5 into 4 divided by pi into 0.865 into 1000 into 129.8 into 0.0025. Okay, now we are getting. Okay, so this is in the meters, right? So diameter in millimeter will be 0.555 millimeters. Okay. Okay, so let's quickly see what we have done. There was a four-stroke engine. Fuel density was given in API. So we discussed that API stands for American Petroleum Institute, and this institute has given some, rules to define the specific gravity, and the formula is given. Okay, so using this formula, we got the specific gravity, and engine power output was given, and engine RPM was given, and specific brake specific fuel consumption was also given. Okay, so brake specific fuel consumption is defined as how much like for 1 unit of power at brake shaft, how much fuel is being consumed. That is called brake specific fuel consumption. Okay, so this is specific fuel consumption was given, and power was also given. So we can calculate the fuel consumption rate per unit time or per hour. Okay, and fuel injection pressure was given and cylinder pressure was given, so we can calculate the pressure difference, and using the formula we can calculate the velocity, because we have the density, right? We have density, we have pressure difference, and we have the velocity coefficient, so you can calculate the velocity. Okay, now the injection duration time is given in crank angle degree, and engine RPM is given. So using these two values, you can calculate the injection duration in SI unit or in seconds. Okay, and using the using these two equations, right? Like you have calculated fuel consumption, fuel injection per cycle in two ways, right? Using specific fuel consumption and using this velocity formula. Okay, so both of these values should be same, so you just make both equations equal and you got the diameter, right? So this was the last question for today. Okay, so in today's session I will quickly summarize that for ACI engine, compression ignition engine, the fuel is injected just before the TDC in the compression stroke. We discussed that for a SI engine fuel, sulfur content should be less as much as possible or equal to zero, because sulfur content reduces the auto ignition temperature, and less auto ignition temperature can lead to knocking. Gum deposition should not be there, and volatility is very important, because uh, if because for good air fuel mixing, the fuel should be evaporated, and volatility is related to evaporation. Okay, then we discussed the paraffins, olefins, and aromatics and naphthenes, and how their octane numbers are, right? And we discussed that aromatics have highest octane number and paraffins have least octane number. Then we solved some numerical. Okay, so we will stop here. If there is any doubt, we can discuss, because we have time, or if there is no doubt, then we will stop.
Thank you, sir.
Okay, thank you. Okay, thank you. We will meet in the next session on next Tuesday. Okay, thank you for joining.
Okay, sir.
Thank you.